as a manifestation of quantum mechanics, we also can look at the specific heat. So let me talk about specific heat a little bit. Okay, we can think about specific heat at constant volume, or we can look at it in a constant pressure. I'm not going to get into those details, but roughly speaking, specific heat, C is the letter we use, is by definition how much the energy changes per temperature. Or like if you pump some energy in your system, how much energy you pump divided by how much temperature changes. Okay, that's the specific heat. Change in E per change in T. Basically, how much you can heat your system. So let's first consider the classical case. Classically, like suppose I have a volume of container V and I have a gas, and the question is, what is the energy of the gas from the equipartition theorem? Like three-dimensional container, like average energy if you want. Yes, 3 over 2 n kT, right? This is the energy. And if this is the energy, C, which is del E del T, is going to be, take the derivative, which is simple stuff. This is 3 over 2 n K. So this is so-called Dulong-Petit law. Basically, specific heat is constant. It doesn't depend on temperature. So this is a monoatomic gas with only translational degree of freedom. Now consider, let's make it a little bit complicated, but still classical. I think I have gas of H2 molecules. And okay, now I need to write E. What is E for H2 molecule from equipartition theorem? So it is it 3 over 2 and kT? How many degrees of freedom do I have for a molecular gas? 5. Okay, so let's count the degree of freedoms. Why 5? 2 rotational, right? Plus, how many translational? 3 translational. Anything else? Exactly. How many for vibrations? Just 1? There's also like this vibration mode, right? For like a given harmonic oscillators, what is the degree of freedom? 2, right? What are they? Yes, okay. So this is 2 plus 3 plus 2, which is what? 7, right? And this is going to be 7 nkt. And from C, what is C? From this, like the formula is given here, it is, okay, maybe it is a little ugly, del E, del T. C, 7 over 2 nk, right? So that's it. Oh, no T, yes, so this is constant. But if you do the experiment, that's not what you find. So let me just give you the experiment. So let's say this is C. So let's say this is T, and this is C. So I have here 3 over 2. I have here 5 over 2 kT, so this is kT, and I have here, okay, this is 2, 5, and 7. 7 over 2 kT. So at low temperatures, what you are going to have is like this, right? So you have a specific heat as if it doesn't know about rotational degree of freedoms. And here is about 200 Kelvin, and it transitions to these rotational levels, right? Here is rotational specific heat, and in about 2000 you transition to vibrational. Okay. So basically, this is what we expect from equipartition theorem, but if your temperature is low, you basically, like, for example, this vibrational mode is like such a high energy mode, you don't see it in the specific heat. You exponentially damp it. And if you are at very low temperatures, you don't even see the rotational mode. You only see the translational motion. Okay? Good? Yeah. Yes?
Is it that there is no rotational motion, or it goes...
There is rotational degree of freedom, but it costs energy to make rotations, right? So there is like, if you remember, it is like Jj plus 1 for this molecule. And there's like an energy gap between J is equal to 0 and J is equal to 1. And to have a contribution to specific heat from this rotational degree of freedom, you need to occupy the higher excited state. But if you don't have enough temperature, right, temperature is too low, you are only going to occupy the lowest state. And the same thing with the vibrational, right? They are like these harmonic oscillator levels. They are spaced by h bar omega. But if your temperature is very low, you are only going to occupy the lowest one, and you'll never see this thermal vibrational mode. So that's the meaning of this experimental result. Good? So this is simple classical stuff, and there is no quantum. So of course, there is quantum because of rotation and molecular levels, but at least statistical description is classical. Now let's consider a solid, and we can consider solid. Okay, let me draw like a one-dimensional version, but you need to generalize it to, like, there are like these springs, right? And so on. Also in x and y direction, like basically a cubic lattice that are all connected with springs. And just to set up the terminology, these vibrational modes, like exactly like we can quantize a single harmonic oscillator, we can quantize like infinitely many coupled harmonic oscillators. And each mode here is, we are going to call them like a so-called phonon. Hopefully this is going to be clear in a little bit. And classically, like for each atom, like there are 3 degrees of freedom, right? And we have maybe I can calculate per atom. Per atom, average energy is going to be like there are 3 springs. Each spring has 2 degrees of freedom, and each degree of freedom comes with 1/2 kBt, right? At the end, average energy is going to be 3 kBt. And if you do exactly like what we did, C is equal to del E bar, del T, you are going to find 3 kB. Again, Dulong petit. But if you do the experiment, here's what you find. So here's the, so this is temperature, this is C. Like at high temperatures, you see exactly what Dulong petit says. There is like 3 kB, and here is your plateau. But as you go to lower and lower temperatures, you go like this, right? So this is, for example, experimental CV of diamond. And it was Einstein who noticed that this is actually a quantum phenomena. Here is like quantum. And rather than this E bar is equal to 3 kBt, Einstein replaced it with Planck's law, right? Exactly like photons, right? whatever you use for photons, he took it and he copied it to here. So basically these vibrational modes of the lattice here, exactly like photons, like light, but in like a different speed of light. Like this is like an effective speed of light, but the statistical description is exactly the same. So this is, does anybody remember average E bar in Planck's radiation formula? I think the first time we wrote it, it must be very complicated, but by now I expect everybody to be able to write it, right? Because there are like two distributions, Bose and Fermi distribution, and one of them, if you multiply with energy, that's the average energy, right? So this is h nu, so the energy of each mode, and you multiply with the average number of photons in mode, that's the average energy of that mode, but in this case, it is the phonons, and Einstein used this h nu over kBt minus 1. Okay, so this is due to Einstein. Yes.
For diamond, how do you interpret the graph?
For diamond,
Yes. It's just, I can't see the.
so it is basically bunch of atoms, right? They are like localized in a crystal site, and they vibrate, right? They vibrate at their local position, and this vibration is exactly like they are connected with a spring, which has some spring constant we don't know. Like this K is not Boltzmann, this is spring constant. Okay.
So why don't we see the vibrational state and the rotational state?
Because this cannot rotate, right? This entire lattice is fixed, right? It is like a gigantic sample. There's like 10 to 23 atoms, Avogadro's number. They are connected with springs. There's no rotation, right? You have to rotate the entire crystal. Whereas in the H2 molecule, you can rotate the molecule. And there's also no translational motion here, right? Because you cannot translate this atom because it costs energy. You cannot take it and freely move it as you wish. Is that clear?
Do you have in mind some molecules which they have rotational other?
Yes, for example, H2 has, this is exactly the experiment of H2. You put in a gas container H2 molecule and measure the specific heat with like calorimetric measurement. And if you can go from like a few Kelvin to a few thousand Kelvin, this is exactly what you are going to find. But if you do exactly the same experiment with, for example, diamond, this is what you are going to find. There's no rotational degree of freedom there. But the puzzle here is like this low temperature region, right? This is what we are trying to explain in the diamond case. So the energy now then is N times E bar, and it's going to be 3N H nu. Let me just copy this like that. And CV is equal to del E del T. And I think this derivative you can take. Okay, this is 3N. Yeah, let me just, okay, right? You need to take the derivative of the numerator and derivative of the denominator, and then you combine all the factors. What you're going to find is something like this, h nu over kBt squared e to the h nu over kBt divided by e to the h nu over kBt minus 1 squared. Good? Is that clear?
No t terms in the numerator.
There is like h nu over kBt. I combined it here. Right?
Lateral 3 comes.
So this 3 is here, right? This is 3. There's like 3 modes for each lattice.
No, in average energy we didn't count 3.
Oh, it is also sorry. So this is like this is one frequency mode. Like this is like one frequency mode for this kind of vibration, right? There is another frequency mode like this kind of vibration, another h nu, and there is another frequency mode like this. In total, there are 3. Okay. So let me just see if this thing makes sense at low and high temperature. So at high temperature, right, if T is large, e to the h nu over kT is approximately 1 plus h nu over kT. This one is going to cancel this one, right? So this is going to be effectively 1, and CV is going to be, this what I found is 3 and K h nu over kT squared, 1 over 1's cancel, and I have h nu over kT. So this is square, and this one is going to cancel this one, and this is constant, which is Dulong petit, as it should be. Whereas at low temperature, at low T, okay, at low temperature you are going to be dominated with this, right? This is, and you can forget about e to the, you can forget about -1, and CV, there's like also power law, but exponential is going to dominate anything else, right? And CV is going to be proportional to e to the minus h nu over kBT. So this one, let me show. At high temperature it works, and at intermediate temperature it also works, but at low temperature it's exponential, right? So there is like a region where it doesn't work. So Einstein is, okay, the calculation is like a step, but it is still incorrect. And hopefully you appreciate the mistakes. And this mistake was fixed by Debye. And if you calculate this so-called phonons in the Debye model, you can get exactly the experimental result. So Debye model fixed so-called Einstein model. But the Debye model is a little bit beyond this course, so I'm not going to show you how it is made. Okay, so this is the last calculation, and hopefully it is not going to take as long. Now we considered classical gas, we considered photon gas, we considered phonon gas, and there's also the last piece. Let's consider electron gas. So again, with quantum mechanics and statistical mechanics. So, because we are talking about specific heat, right? In the case of diamond, we don't need to consider, so diamond is an insulator, you don't have free electron inside it, but if you do the specific heat measurement with like a metal, right? There's like these crystal vibrations because of like crystal lattice, but there's also like free electrons. That's what metals are by definition. Then you also need to calculate the contribution of free electrons to specific heat. And if we think of electrons like classical description, right? Electron is a point particle, and it, in 3 dimensions it has like 3 degrees of freedom. And if you calculate CV, specific heat, what you are going to find is it's given by Dulong petit, 3 over 2 and K. And of course, this is not the experimental result. For once, electrons are quantum particles and they obey Pauli exclusion. So electrons obey Fermi-Dirac, which is going to be F for any given energy. You have e to the E minus E Fermi over kBT plus 1. And for some reason I cannot. let's consider electrons in like 3D box potential, and their energy is epsilon and x and y and z, right? There are like 3 quantum numbers in 3. I think we did this exercise, and the result was 2m. If the size of the box is L, we are going to have pi square and x square and y square plus and z squared. And x, y, and z go from 1, 2, 3, and so on. They are integers. And we said, okay, let's exactly like the 3-dimensional case with the photon gas, or like black body radiation, let's call this n squared, right? This is in the photon gas we had like jx, jy, and jz, and we had like an arbitrary j that could be in any direction. Here we are going to use n index for that, and here n is going to be equal to an x square and y square plus and z squared, and En is equal to h bar squared over 2ml squared pi squared n squared. Now I need to calculate the number of modes at a given n. The n is equal to, okay, the picture is, let me just pull this a little bit down. Let me draw a 2-dimensional picture. You can generalize it to 3D. We have these. Something like that. Maybe one more here. And we are considering like a shell here. Right? So there is like some n, and there is some dn. And number of states in a given shell is going to be first 2 for spin, and in 3-dimensional box we have to multiply it with 1/8 because we only take the positive quadrant, and the volume of the shell is 4 pi n squared dn. Good. But exactly like in the black body radiation, we need to go from the n variable to energy variable. And it is given here. So this is E. And if I take the derivative dE, I'm going to have 2n dn. And I can also write n in terms of E. This is going to be 2m over h bar squared L squared over pi squared. So there's this root, and there's also a root of energy. So this guy, I'm going to write it like n and dn. So this one is going to be, okay, cancel this with this. So this is going to be 2. Okay, let me write it. So this is gn dn, and this is pi over 2. N is equal to here, like that. And n dn is equal to the epsilon divided by this entire thing. Good? Okay, this is a little bit easier to do. And now some cancellations. If you do all of these, what you are going to find is I will call L cube volume. This is going to be V divided by 2 pi squared, 2m over h bar squared 3/2, and there is root E and dE. And I'm going to assign this to density of states in energy space, dE. Is that clear? So this is exactly what we did photons, but in a different variable, epsilon. But now we are trying to do something a little bit more complicated. We have like a fully quantum electron gas, and we are trying to calculate the total energy so that we can take the derivative and find the specific heat. So let me do that. First, let's find so-called Fermi energy. And to find that, I put T is equal to 0. Okay, I am trying to calculate the Fermi energy, and to find the Fermi energy, I need to calculate total number of electrons, which is going to be from 0 to infinity, the epsilon. So this, okay, G of epsilon and F of epsilon. But F of epsilon is at 0 temperature, F of epsilon is just a step function, E Fermi minus E, right? Anything below Fermi level is occupied, anything above is unoccupied. So this is going to be from 0 to E Fermi, the epsilon, G of epsilon. So I've taken care of this distribution. But you can see this thing is given. So this is going to be equal to, just copy this here. And if you integrate epsilon, it's going to be 3 over 2 epsilon Fermi 3/2. Is that clear? I just have taken the integral here. And from here, what we find is, okay, you can see this volume can go to this side. And what we find here is E Fermi is proportional to square root of n to the power 3. So this is energy. And the calculation, the next step in the calculation was calculation of energy, E. And the energy was exactly like that. Let me just copy here. And we just multiply this with epsilon, right? And the result is going to be, let me just write it. Rather than square root of epsilon, you are going to integrate E epsilon to the power 3 over 2. And the result is V over 2 pi squared, 2m over r squared, 3/2, 5 over 2 E Fermi. So one thing you can find from these two, you can take E divided by n. The energy per particle is going to be, you can see everything is going to cancel, right? Volume, 2 pi, this 2m h bar squared, everything cancel. What remains is this kind of like famous factor, 3 over 5 E Fermi, which is constant and independent of T. So if something is independent of T, if I take the derivative, then del E del T seems to be 0, seems like no specific heat. But this is actually incorrect. So what we need to do is, okay, let me tell you how it comes about. First of all, E Fermi in metals, E Fermi is order of 5 to, so this is, by the way, the energy we see in the photoelectric effect. In the photoelectric effect, what we call work function is actually Fermi energy. And it is order of electron volt, something like 5 to 10 eV. Whereas room temperature, kBT room, you can multiply room temperature with kB. This is like an energy unit, and it's about 25 milli electron volts. Because this is the definition of specific heat. Specific heat, by definition, is change in energy by change in temperature. Okay. And since kBT much less than E Fermi, that says all electrons are frozen in the Fermi surface, right? They seem to have no contribution. However, what happens is like what you can do is you can actually take the derivative before you take the integral. So let me just show you that. If you take the derivative before you take the integral, so this is del T, and this is the only temperature dependent quantity here is this del F del T, and F looks something like this. Right. So this is 1, and there is like a Fermi level. It just transitions from 1 to 0, and I have like, okay, this is, yeah, you can relate this to derivative of epsilon. Let me not get into that, but what I want to ask you is like, what is the derivative of step function? If I give you a step function like this and ask you to calculate the derivative, it is another famous function. What is it? Delta function, right? The derivative is going to be delta function like this. And the width of this delta function is going to be order of kBt. And from here, so this CV is proportional to kBt. And this is electron contribution to specific heat. But of course, for this to take place, you need to have electrons, and this is valid for metals. Okay. Maybe I can stop here. Sorry for the delay. Any questions or comments?